what we saw last time and what you practiced also with Dr. Friedman was to do your uncertainty quantification. That is to push uncertainty through your model in some way, okay? And we saw different ways of doing it with Monte Carlo, quasi Monte Carlo, or other different integration methods, or by building proxy models, okay? And for these both to do the integration methods properly and also to do build these proxy models properly, we needed to have some good coordinates, so to speak, some good random variables in which to build all these models. Okay, and I showed one way on how one could build a set of independent normalized Gaussian random variables, which would, and their polynomials in them would span the whole space. So we can expand any other random variable which depends on them in these coordinates. And then, of course, the first thing was to represent the input in these random variables, in these new random variables. Okay, we call them theta. And then push this through the model in different ways and build a proxy model for the response, either for the state of the system, U, or for the quantity of interest, okay, which was also then written in terms of functions of these basic random variables. As functions, we chose polynomials because this was the classical choice, and this is also the natural choice when you're working in an algebra, because, of course, many other functions can be used. Okay, so this is where we stopped, and that's where we want to go on now. Okay, so now it will be more about multidimensional random variables like we had there, like the state vector or the vector of input random variables, which we had to use, which came actually from a random field. And today we're going to speak essentially about model rejections. So the question is, which random variables do we need? Okay, so there's probably infinitely many random variables, and these are dimensions. Each random variable is a dimension in our computation, either in the collocation or regression or in the integration, whatever it turns up as a dimension. So it is additional numerical work for each actual random variable. So we'll try and have the number of random variables at a minimum, and this is what's going to be now on how to pick the important ones. Okay, so this is the overview of this lecture. So I'll remind you once more what we have been doing, linear methods and expansions, so that we work in linear spaces. Okay, we'll define what are random vectors, also random vectors in infinite dimensional spaces, so which means random fields, random processes, and things like this, or other abstract random vectors. Okay, and we'll see that this is connected with linear mappings. And when we analyze these linear mappings, we can find decompositions of these linear mappings. So linear mapping is something which has been known for a long time. There's a lot of techniques to analyze them. And when we use this, we can see that we can do something which is called spectral decomposition, which probably all you know. And we can do something very similar, what's called singular value decomposition. And this leads to something which is called the Cahoon-Loew expansion of these random vectors, okay? And this will pick the important random variables. So this is about characterizing input random fields, input random vectors, input random quantities in a better way, is with as few independent random variables as possible, okay? And so I'll add at something at the end, and what are other characterization or things we need to characterize random vectors, random fields, and things like that. Okay, good. So just as a motivation is, so we've been expanding what we're just saying, we're expanding things in IID variables theta, and we use polynomial chaos. As I said already, other functions than polynomials can be used, for instance, neural networks or something like that. But we'll stay with the polynomials because this is the simplest and oldest example of this, okay? Good, so the question is, how many random variables do we need and which ones should we take? Okay, so there's potentially infinitely many of them, okay? So, but we want to use as few as possible, okay? The way I presented it in the last lecture, they were picked without regard to the problem, okay? Well, now we will change this and we will look exactly at what do we want to approximate and that's going to pick these random variables, okay? So we want to avoid to use too many random variables and too high degree polynomials. So all of this blows up dimension, blows up the numerical work we have to do, okay? So this is model reduction for stochastic systems. And the main thing I'm going to show is related to something you probably all know, and this is proper orthogonal decomposition, which is sort of the same thing in blue, so to speak, okay, or in green or whatever other color you want, okay? So it is really mathematically absolutely the same thing. Good, so we've seen PCE representations, okay? So let's say here for the state, the same thing goes for the input, okay? So we represented this random vector actually by these coefficients. And these coefficients were coefficients with these functions in these random variables. And now the question is which random variables to pick and which polynomials to take, okay? So, and equally, it was represented by this tensor, which is just collecting these coefficients in a different way, okay? Now, there's m of these, this expansion has length m, okay? And the dimension of u is n, okay? So if m, for instance, is larger than n, then it's obvious you don't need all of them because they have to be linearly dependent, okay? So that's the first thing where you see, aha, there may be something where we can save something, okay? Good. So, and then the question in general comes, of course, which is the separated expansion, which has the fewest number of terms. We call these expansions separated because this is a random vector and it's split into constant vectors times scalar random variables, okay? And the whole thing is going to live from these separated expansions. What this means formally, that this object is in a tensor product space, okay? And tensor, this will come in a later lecture. This tensor view allows to reduce the amount of information you have to work with, okay? This will be especially become true when we look at this big tensor of degree j, okay? But this is going to be in one of the last lectures. Good. So, and the other thing is what I want to stress is that we work with linear methods, okay? So this is a linear, lives in the span of these u alphas, okay? And so there is nothing else which really we can impose as conditions that which u, for instance, or any input we put in to have to satisfy. For instance, if we require that one of them would have to be positive, it's difficult to do with linear expansions like this, okay? So that typically will have to be transformed in some way. And this will come in, I think, tomorrow's lecture, okay? So, and we actually expanded each component here separately. That's when you look back what we did, we expanded each component separately, okay? But the question is, when we look at it all together, can this be a way of reducing the number of terms here, okay? One, I pointed out already, if there's too many terms in this expansion here, then obviously it's not necessary because this is linearly dependent, the number of vectors here. And this only you see only when you look at the whole, at all of them, not just at each component, okay? Good, and now we will connect this expansions like this. We will, or parametric objects, see this u depends on the parameters theta, okay? So parametric objects in general, they can be connected with linear maps, okay? Because this can be any dependence on theta, but linear maps are linear maps, and that's something really nice to analyze, okay? So this is the advantage of that. Good. So let's first look at what is a random vector in a vector space, okay? A random variable in a vector space. A random variable is a vector space is a random variable which takes values in the vector space. That's the easy thing to say, okay? But what does it mean more concretely? Okay, so if this is a finite dimensional like Rn, then you can say each component is a scalar random variables, and we finish with that, okay? And this can be extended to time function stochastic process where you say for each t, for each moment in time, this is a random variable, or random fields where you say for each position x, this is a random variable, okay? Problems with this kind of definition occur for abstract vector spaces, okay, where you don't have the interpretation that this is a function or whatever. So that's needed sometimes too, okay? Another way to say that this is a random variable is to say I take something in a dual space and take the scalar product, okay? I take the dual vector, apply it to this random variable. Of course, outcomes for each theta is scalar. So this is a scalar random variable, okay? And that's another definition to say this is a vector-valued random variable. If you take this inner product for any kind of v, then you get a scalar random variable. Okay, and of course, if this is a finite dimensional space and I chase the unit vectors in direction k, this recovers this definition. Okay, but this one is much more general. Okay, and it allows for weak or generalized random variables. Okay, like generalized functions, the delta function, and things like this. This way we can allow very wild, so to speak, random variables. We will not go in this direction, but I just mentioned this. Okay, yet another definition starts with this representation, which we already saw, yeah, and we say anything which can be represented like this is a vector-valued random variable. Okay, mathematically, this says that this is an element of this tensor product space. Okay, so in finite dimensions, they are all the same, but in infinite dimensions, they are not. Okay, and this is the most general, and this is a more restricted. Okay, and this again applies only to concrete objects, like functions in time or fields or things like this. So we will mainly use these last two computationally, okay? But this is the traditional way of looking at that. So we're looking at it a little bit different way because we want to do these expansions here, okay? Good, so let's look at parametric objects in general. And so think of R of P. R is a generic parametric object. P is a generic parameter. In our case, P was a random variables, okay? But these parameters appear also in other contexts. For instance, if you have to optimize or minimize some measure of cost or control the behavior of some system, then the P may be control parameters, or there may be random as we had, okay? Or there may be something which we want to identify, and this is going to come in later lectures when we do identification, okay? So they can have all these roles, okay? And some typical things is, for instance, the solution to a high fidelity model where you will want to build a reduced order model, okay? Or a parametric reduced order model, or a solution to a parametric PDE, like the example we're always looking at, this flow through an aquifer with where the conductivity field is their parameter, okay? Or this can be an input to a computation, a random tensor field, for instance, like this diffusion tensor or conductivity tensor, which we're talking about, yeah, for this example, okay? It could be actually an operator, okay? Okay, or it can be something which is today called a digital twin. So that is if you have some important part of infrastructure, let's say a dam, you have a mathematical model which tracks it, okay, and which collects all the information, maybe automatically, of the sensors and updates them, okay? And this information of what's being updated are parameters, so they are really updated, okay? So these are examples of parametric objects. So now assume we have one, so what are we going to looking at? One is the range. So as P varies, where does R of P vary, or Y of P? Okay, this is important in design control. Control means to reach a desired quantity of interest by changing P. Okay, and this is really a special case of optimizing the quantity of interest by changing P and finding an optimal P check here. Okay, or uncertainty quantification. And the P's are random variables, and we want to compute the expected value of that. For instance, this is what we saw already. Okay, so the questions are: what is the theoretical background for these parametric models? And what possibilities do we have to choose parameterizations and obtain a reduced order model? And how can we preserve structure? Okay, so these are important things. We'll just touch a little bit on this last one, and it will be mainly tomorrow where we talk on that. Okay, good. And just take a little example here so we see where we're going. Assume, for instance, that our space where the parameters come from has just 3 values. Okay, so it's finite. That makes it very simple. And that the parametric object has 4 dimensions, so it's a 4-dimensional object, okay? So the P can take 3 different values, and they're listed here. So this is P1, the blue one, P2, the red one, and P3, the green one, okay? And I arrange this here in the matrix here. And of course, this matrix holds the same information as this function R of P, okay? Obviously, because it's all in here, okay? But a matrix, we know, corresponds to a linear map. So because this here corresponds to a linear map from R4, to R to the power P, which means all functions from P into R, which is the same as R3. okay, here, because there's only 3 values, okay. In general, this is a space of functions, all the real valued functions on the set P, okay. So, and how does it look like? So for any U in R4, okay, that's the space along this dimension here, we can look matrix times vector product. What is it? Well, it's actually the inner product of this parametric object with U, and it gives us 3 values. Yeah, a function phi, and it has 3 values at P1, at P2, at P3. Okay, so this function phi, that's a 3-dimensional vector, is the result of this. Okay, so when we take this linear mapping and apply it to a vector, we get a scalar function. Okay, and the scalar function is a weighted average of the values which this thing takes. Okay, so knowing this or knowing this is equivalent. Okay, and this turns out to be true also if P is infinite or U is infinite dimensional, and that's a way to go to analyze things like this, because this matrix now, as the linear mapping, can be analyzed. Okay, good. Let's go to the next one. So this is now the associated linear map we're talking about. So we have a parametric object, okay, and we assume that U is the dense, the closure of the span of this. Okay, so there is no subspaces left which are not touched by R. Okay, good. So what we are after is our representations of R. We want to represent R in some simpler way. Okay. And we are after other parameterizations. So the parameter set P may not be good. I've been talking about this already, that the parameters you presented with originally are often not good parameters. Okay. So what we do to each function, to each such function, we associate a linear map, okay, from this vector space U, where this little R maps into, to another vector space, which I call R tilde. And R tilde is a space of functions. And how does this map work? Well, it takes a vector U and makes the inner product of this random vector times this vector. Of course, this gives a scalar random variable, okay? In our case, but it gives a function on P, okay? So an object in here, okay? So, and then of course this, because this is a subspace, this maps onto a subspace, okay, which we call R tilde. Okay, these are all the real functions of P which are hit by this mapping here. Okay, so, and by construction, of course, this is an injective mapping which I've just built here, because it has the same information as this R of P. Okay, and now what I can do, I take the inner product which I have on this space, which was used to build this mapping, I take it and pull it back with this injective mapping, okay, to build a inner product on this space of functions. Okay, I take the same inner product and transport it there. So the inner product from U is transported onto the space R tilde. Okay, and we call this with a little index R here. And it turns out this R is unitary on the completion. Okay, so it's whether I look at this or this doesn't matter. And this is something which is very well known in analysis. So I digress a little moment to look at this. So this guy is called the reproducing kernel Hilbert space. Okay, and the inner product of this parametric object with itself is called the reproducing kernel. Okay, and the reproducing property is following: if I take the inner product of any function in this space R, okay, with this kernel at a position P, I get exactly this function evaluated at this point P. So this acts like a delta functions on these functions R in R here. Okay, and it turns out this space is actually the span of all of these here. Okay, so this is actually used in something which is called support vector machines. They're used for machine learning and classification. Okay, where you want to classify different subsets of P. So one set of parameters this, and the one set of parameters is this. Okay, and then typically this map is not given, but you choose it. It's called the feature map. Okay, and the whole procedure is called the kernel trick. I think what you're going to see now. Okay, so, and for us it's important we can use this reproducing kernel Hilbert space already to represent our function R of P. Okay, our vector-valued parametric object. Okay, in our case, a random variable. Okay, how can we do it? Well, we just take a complete orthonormal system, okay, in this space, and then we pull these orthonormal vectors back with this unitary mapping. They're still orthonormal when we pull them back, okay, and then we just expand. Now these are orthonormal vectors in U, and then we just expand R of P in these orthonormal vectors UM, of course, with coefficients which of course depend on P. So now we have a separated representations. The U's are vectors in the space U, and these are scalar functions of P. Okay, and these are kind of coordinates, okay, on P, and you can say they're new parameters. And the nice thing is this R of P is linear in these new coordinates. Okay, so that's the important thing. Good. Alternatively, of course, we can choose a complete orthonormal system in U and then push it over to the space R or Q. Okay, but the problem is now in both of the cases I choose. It's arbitrary which complete orthonormal system I choose, so it's not really adapted to our mapping, so it's not really good. We're looking for good or important parameters. We don't want too many, okay? I don't want this M to run in the millions or something like that. 10 or so is much nicer, yeah? So we're looking at representations in other vector spaces, okay? Good, and just to put this in a bigger context, okay? The set P, where the parameters come from, is just some set, okay? Whereas R, which I replaced it with now, because the coordinates here, these y's, they come from R, they have scalar functions of P. Yeah, this is a vector space, so that's a much nicer object to work with, okay? And this is one of the big successful ideas in mathematics. If you have a complicated set, you assign an algebraic structure to it. It can be groups or vector spaces. In this case, it's a vector space. Okay, and this is done in algebraic topology, but in probability and so on, we'll see this. Okay, and in kernel classification, it's done also. So it's done to separate, for instance, two subsets in this set here, which maybe look very complicated to separate them, and we can replace this by a separating hyperplane. Okay, so that's very easy. We take a hyperplane, and on one side is this, and the other side is this. Okay, and then we know which belongs to P1 and which belongs to P2. If P1, then R of P1 has to be on this side of the hyperplane, or otherwise on the other side. Okay, good. So what does this look like? I think I have a little picture here for you to see this. Okay, so I took this from Wikipedia. For instance, let's say you want to separate these dots, the hollow dots, from these filled dots. Okay, so this red line would be something which separates this subset from this subset. So the whole square is the set P, and this is the subset P1, and this is subset P2. Okay, and what this does, it straightens this out in some way like this. Okay, so now to this transformation, this kernel trick, the feature map, mapping this into a vector space, it looks like this. So the hollow points, they lie here, the filled points, they lie here, and I can take a straight line, which is a hyperplane in the two-dimensional space, to separate them. Okay, and I just have to look what's left or what's right of the line. Okay, another example is, for instance, these points. So there's blue points and red points. And you see the red points are inside this circle. So this makes it simple, you know, the circle, it's not so complicated. It could be a more complicated set. But see what it's done with this feature map here. So it lifts these points up, okay? And then the blue points are higher than the red points. And now you can put this green plane in here, okay? A hyperplane in 3 dimensions, and it separates the red from the blue points, okay? So this is this kernel trick which is used in supporting vector machines. So we'll come back now to our problem here of finding good approximations, okay? So assume we have another inner product, and the problem here was, just to remind you, the problem with this space here, with the reproducing kernel Hilbert space, was that the inner product on the reproducing kernel Hilbert space was exactly the same as this on the space U. It had no new information. It didn't tell us especially which parts of P are important or not, okay? So assume we have something to tell us which parts on P are important. And the way we use it, we say we have an inner product on the space of functions, okay, on P, scalar functions. And something is important. when it has a big norm when I compute a function is important when it has a big norm in this inner product. Okay, so take the product of a function with itself and then the square root, that's a norm. Okay. If this is a measure space, for instance, like in our case, a probability space, then of course we'll set this Q to be just the L2 space on these functions on P. Okay, good. And then we can define something which in probability is called the correlation operator, but it's in general something like this. And we take it like if we take two vectors in U, we can define this bilinear form, okay, which is just R of U times R of V, and then taking the inner product here in Q, okay. So this is linear in U and linear in V, so it defines a bilinear form, and we know such bilinear forms define linear operators, and this operator I call C, okay. In this case, it turns out it looks like this. We'll come later to this. I think this is going to be also in today's lecture a bit later. Okay, okay, good. And we have to see that C, what does C look like? Well, C is exactly this. It's R transpose times R. Okay, so this is what it looks like. So it's a symmetric, positive, definite mapping it comes. Of course, we can look at this factorization. That's the factorization on the set of linear mappings on the space Q. Okay. It turns out both of them are self-adjoint and posit-definite. That means the spectrum, that set of all eigenvalues and more in infinite dimensional spaces, we have generalized eigenvalues, is positive, is real and positive. Just to remind you, eigenvalues of linear mappings can also be complex. Okay, but when they're symmetric and self-adjoint, then it's real. And when it's positive, then it's real and positive. Okay, so it lies in here. That's going to be important for what we're going to do, okay? So just let's look at the finite dimensional case. Assume this is a random vector in some Rn, okay, like our example in the beginning where we had the state of our system depending on random variables and we had n components, okay? Good. And this mapping then looks like this here. We've seen this already, okay? And assume for simplicity that the expected value of this random vector is 0. Okay, so then this is the covariance matrix, which is defined by this. Okay, so what is it? U transpose CV. Now we try to find out what is C. It's this inner product. Okay, and this inner product is given now here by the expected value. So it is the expected value of RU, which is this, and RV, this is this, and the product of these, and then taking the expected value. Now, because U and V are constant, I can take them out of the expected value, and I have this here. And this guy here, in of course, in the middle, is called the correlation matrix. Okay, so and this is exactly the matrix we're looking for. And we compare these two expressions, we see this is the matrix. Okay, so the C looks like this here, or written in a fancier form with a tensor product like this. Okay, and it's clear that it's symmetric, and it's clear that it's positive definite. Okay, good. Whereas if we were looking at this is R transpose R, we were looking at R transpose, it turns out it would be an integral operator. We'll see this later. Okay, and the things are even simpler when this is finite, because then this mapping R is actually a matrix. This is the example I showed at the beginning. Okay, so let's assume that this is a matrix. And this looks like this, R transpose times R, okay? And the CQ would look like this now, the other one, R transposed. And they, of course, because they're symmetric and positive definite, they have a spectral decomposition, okay, like this, with V being a orthogonal matrix, this being a diagonal matrix of eigenvalues, of positive eigenvalues. And the same here, this is the set of eigenvalues of this guy here. And from these together, we can piece together what's called the singular value decomposition of this mapping R. It's this matrix S, which are the eigenvalues here, times the square root of this matrix. It's easy to take. This is a diagonal matrix with positive entries. So it's just the square root on each diagonal point, okay? And then we take these vectors V, which come from here, okay? And it turns out, of course, these are unitarily equivalent to multiplication, which is what we see here, by this diagonal matrix lambda, okay? Writing this in a different way here, it looks like this. So it's another way of writing this expression here, okay? Where the VMs are the columns of this matrix V. And then this R is written like this, okay? So it's another way of writing the singular value decomposition. And what we see here, we have vectors which are in the vector space, And we have guys Sm, which you remember are scalar functions on our set P. Okay, and here come the eigenvalues, of course, because they're positive. And there's the largest one. I can order them by size. Okay, so first of all, this I can use the singular value decomposition. I can use this to do a representation. Okay, I know the transpose mapping, which maps from the space of functions Q to U, looks like this here. Of course, just these two things here interchange. That's the only thing here. Okay. From this, I can glean right away that R of theta can be represented this way. Okay. That's something we had before with an arbitrary orthonormal system, but now we have a special orthonormal system was chosen as the eigenvectors of this correlation or covariance operator. Okay, and because they have both unit length here, okay, they're orthonormal. This tells me how important each term is. With lambda m big, the term is important. With lambda m small, the term is not important. And again, it's linear in these new coordinates. Okay, and the first ones are the most important coordinates because that's where lambda m is big if I sort it like that. Okay, so this is what I'm saying here once more. Because it's symmetric positive definite, I can order these here. Okay, these vectors are orthonormal. Okay, so these guys have zero mean and unit variance. Okay, the way to compute them is by projection, by computing this here. Okay, so this is this mapping R of Vm again. Okay, and I can order them, decreasing size. And then this expansion is called the Cahoon-Loewe expansion. I've written here, abbreviated KLE. Okay, you'll see the name of it. And I can truncate it when this lambda m becomes small. Okay, so then it's an approximation, and I stop it at rank R. Okay, and it becomes a reduced order model. So what I've reduced now, I've reduced the number of uncorrelated random variables, which are these SMs, which I need here. Okay, so I have fewer. Okay, and observe please that the way to do it was to go, if we look back here, via this mapping RT, and R and RT, they were a factorization of this matrix C. Okay, so if I take any uncorrelated random variable C, okay, and multiply RT by C, I get a random vector, and this is random vector, so I take these here with zero mean and unit variance. Okay, this vector here, see, I make a random vector R tilde. This vector has the correct covariance, like the one we see, because if I compute what it is, it's this here. I can pull the R out because it's constant, and I get, because this is the identity, I get C. Okay, so one thing how people like to do is to take Cholesky factorization for that. Okay. Good. So this is true for any factorization, as I was just saying, for instance, for the Cholesky factorizations. Okay, so this has the correct covariance. This is the same computation as you've seen just before. Okay. The problem is with the Cholesky factorization, it doesn't tell you which C's are important and which are not. Okay, but the KLE can be truncated in a controlled way, and this gives the best R-term approximation, best invariance in our case. Okay, with just R random variables Sm, and they are uncorrelated. The problem is they are only uncorrelated and not independent. Okay, but now we have R of them. Okay, and we can now expand these guys here in independent Gaussians, but we only need R of them. Okay, so it's a model reduction now. I need fewer of these thetas. Okay, I can take the first S1 and then make it into a Gaussian. Okay, then I can take the second one and make it also an uncorrelated Gaussian. Okay, this is called the Rosenblatt transformation. It transforms these guys here into independent Gaussians. Okay, and these independent Gaussians can be used now here as we did before in our expansions, but now that we know what importance they have. Yeah, the first theta is the most important one. The second, because it belongs to the highest eigenvalue. Okay, good. So what I can do, I can explain these Sm of thetas into a polynomial case and insert this into the KLE expansion, which we have here. Okay, so this is the mean, okay, times a constant, which is 1. So formally it looks like this. So I can start the sum by 0. That pulling this in here makes the expression shorter. So this is what we had before, lambda m times Sm. So an Sm was replaced by this here, okay, times Vm. Okay, and now we have an expansion in here. It was an uncorrelated. Now we have an expansions in these independent random variables, okay. And we know the first theta is the most important, the second most important, and so on. Okay. Good. So this was a characterization of this random vector. So that let's look at the different ways we've characterized this. Okay. So we've characterized this as a random vector, for instance, through its moments. You've only seen k equals 1 and 2, because 1, of course, was the mean. Okay. And 2 was the covariance matrix. So covariance matrix comes in here as a second central moment. But of course, I can go k higher moments, and I get tensors of degree k, which may be higher than 2, okay, which characterizes. So this is the moments. So when we have a vector, the moments are tensors. The moment of degree k is a tensor of degree k, okay, as you see here. Good. Another way to characterize it was by its PCE coefficients. Okay, but this was again in random variables theta, which really had nothing to do with the problem. They were picked arbitrarily. Okay, so what we can do better is to take the KLE PCE coefficients, which came from this expansion here. Okay, so it's called, of course, square root of lambda m times this here. Okay, so there you have it. These are the coefficients. Okay, look at these SM alphas, which comes from the expansions of the SMs. The uncorrelated random variables times the square root of lambda m. That characterizes this random vector. Okay, we'll now look at a few other ways what is important here to say what we're looking at. Okay, so we'll look at the cumulative distribution function. That's something we looked already in the case of scalar random variables, the probability density function, which will be the derivative, and the characteristic function. Okay, and the cumulative expansion of random fields. So we saw this, what this looks like now, when this guy is a finite dimensional vector. Okay, now we go into an infinite dimensional space where we have fields, and where this R is not a matrix. Okay, so C and R, of course, are not matrices anymore. So will look like what they look like there too. I already hinted that they will be integral operators. Okay, good. So now let's look at the cumulative distribution function, first of all. So what we do, we take an infinite rectangle. Let me see. Take a tool here. I'll take a pencil. Okay. So if this is, for instance, in 2D, this is x1, and this is x1 coordinates, the 2 coordinate. And now we have a point here. And so this is x1. Sorry, this is x2. It's very difficult to write here. So this is x2. And of course, this is x1, this value here. Then this t is this rectangle here. And everything down here. Yeah. So that's this rectangle. Let me go back to, I'll go back to my hand here. Okay. So that's what this rectangle looks like. And now we look at the probability that the random vector is in this rectangle. You have only 2 dimensions, but this is up to n dimensions. So that's what we're going to look at. So first we make a new random variable here, 1. So a function 1, which is 1 here and 0 out here. Okay, and then we take as argument this random variable. Okay, so this function produces a 1 if the random variable is inside this rectangle and 0 otherwise. Okay, this is how we did it before with a semi-infinite interval. Okay, now we have a semi-infinite rectangle here. Okay, and now we define the cumulative distribution function to be just the expected value of this random variable. And that's, of course, the probability that the random variable R 1 to Rn is inside this rectangle, okay? And this function of x, here we only have x, the coordinates x1 and x2. This function of x we call the cumulative distribution function, okay? And of course, you can see if x goes to infinity, it means all components go to infinity, then it goes to 0 because the probability of this being happening goes to 0. Whereas if we go to plus infinity, of course, then the probability of this happening goes to 1. So the value is 1, okay? And if y is smaller or equal than x, meaning that all the components of y are smaller than x, okay, then of course fr of y is smaller than fr of x, okay? And I think I can clear this now, okay? So you can see this, and the weak derivative of this guy here, corresponding to that's called the probability density function, okay? So the variate probability density function. Good. So these are two things which work, by the way, in finite dimensional vector spaces like Rn. There's difficulties with these guys in function spaces and things like that. There often is no density. So, but the characteristic function, okay, is something which also exists in infinite dimensional spaces. So what is the probability characteristic function, okay? It's another way to describe this random variable. We saw already, I mean, we saw the moments and so on. We saw the cumulative distribution function. We saw the density, but the density is a function of x, okay? And of course, we know another way to characterize the function of x is through its Fourier transform. And that's what this guy here is. So in general, it's defined like this here, okay? It's the expected value. If I take this random variable, remember, this is our linear mapping capital R of xi, giving a scalar random variable. We multiply it with I, okay? And that takes the exponential of it, of course. This is something of absolute value 1, okay? And then we can take the expected value of it, okay? Good. And of course, this is something which is in the unit circle, yeah, because these guys lie on the unit circle. The expected value is a combination, an average of them, so it's something which lies in the unit circle. So this function is always in the unit. It's a complex valued function, and its value is always in the unit circle, okay? And if this guy has a density, then this can be rewritten like this. So this is, as you see, the Fourier transform of the joint density, okay? It is not normalized, so it's actually the inverse Fourier transform, okay? And it's not unitary, so otherwise you have to have a factor here, okay? Good. But that's what's called the characteristic functions in probability theory, okay? If I added probability in front of the name because characteristic functions appear in other cases, and they are also used for this guy here. Okay, it's called the characteristic functions of this rectangle. Yeah, so unfortunately, the name appears many times. Okay, so to make this clear what it is, I call it the probability characteristic function. But in probability theory, it's just called the characteristic function. Okay. Now, because these are Fourier transform each other, there's certain relations between the cumulative distribution function, the probability density function, and the probability characteristic function. This guy here. Okay, and this is just comes from Fourier theory now. Okay, so what are the relations? Of course, this is what we had before, because this is the derivative. This guy is the integral of this here, from minus infinity up to that point. Okay, and this is not just 3, but n integrals, of course. Okay, and from the definition of the probability function and the characteristic function, we have, because if we take c equals 0 here, we're going to keep c equals 0. This guy is 0. On an exponential of 0 is 1, okay? So then means the value of the characteristic function at 0 is what is this? Is just this integral here. Well, of course, because this is a density, it integrates to 1, okay? So that's the limit of this guy as x goes to infinity. So the value of the characteristic function at the origin is always 1, okay? This comes from this being the Fourier transform of a density, of a probability density. Now, of course, our probability density is a real function. Fourier theory tells us then this guy has to be a Hermitian. Hermitian meaning the following. If I go to minus xi and take the conjugate complex, then I get the same thing. Okay, so this bar means the conjugate complex value of this here. Okay. So in this way, it's like a symmetric matrix. Okay, a symmetric, or let's say a Hermitian matrix, a complex matrix, and where you take the transpose, you also have to take the conjugate complex, and it's the same thing. Okay, so it's like a Hermitian matrix. It's all in functions, we call them Hermitian. Okay, and it's also, of course, our density is also positive, and that means that the characteristic function is what's called positive definite. It's like for matrices. Which means for any other scalar function, if I take the inner product of this guy written as a matrix, so it's like C is one index and eta is another index instead of a sum. We have an integral here now. If I do this here, okay, sorry, this was wrong here. There should be a key. Oh, no, I have a key here. So because these are complex functions, I have to take the conjugate complex. So if I do this, there's something which is always larger or equal than 0. And this larger and equal than 0 corresponds to this larger and equal than 0. Good. So these are relations. Okay, now let's look at how we characterize stochastic processes in random fields. Okay, so this was for vectors. What we did now, we are now a bit more difficult. Instead of a random vector, we take a random vector in an infinite dimensional space. Okay, and I will look at stochastic processes just like at a 1D random field. So I'll treat them all equally. Now, the random field can be looked at either as a collection of random variables indexed by the position in space, or you can look at this as random space functions. So for each omega, you get a new function, a new realization. Okay, there's two different ways of looking at them. Okay, in traditional stochastics, the first one's the normal one taken. We're taking more the second view. Okay, it's more a functional analysis point of view. Okay, now it turns out as characterizations, the distribution and densities, they are problematic in function space. That does not work. Okay, but there's some other pointwise characteristics we can look at. Okay, which are very similar. Okay, and one is the mean of such a random field. Okay. The mean means at each point x, I take the expected value. Okay, so that's this guy R bar here. And then, of course, I can build the mean-free part, which is R tilde, by subtracting the mean. Okay, so this is a deterministic function. Subtract it from a random function here and give me another random function which has mean 0. Now I can look at the distribution of R tilde or R at each point x. Okay, so we know how to do this. It's just a one-dimensional random variable now. Okay, what's the probability of this being less than s? And we saw this before. We saw this in several dimensions just a couple of slides before. So this is the distribution of the random variable rho x here. Okay, this kind of row. There's another row here. Okay, good. And we can also look at something which is called the correlation kernel. And you see that's the second moment of mixed moment of this random variable taken at two different points. Okay, so that's something which is called a two-point correlation. Okay, and of course now we can look at higher moments of this here, and this would be here. So we take points x1 to xk and take the expected value of this guy here at points x1 to xk, multiply and take the expected value. Okay, and that gives us what's called the k-point correlation function. Okay, but this one is one of the most important. Of course, the mean here, that's the first one, and this one here, the second moment, these are the most important ones. Okay, the characteristic function is something which is still defined. It becomes now a characteristic functional. Okay, because it's x on a vector space. Okay, because if this has values in some space u, okay, then we take something from the dual space, and I take the inner product of this guy here with R of omega. Of course, this is a scalar depending on omega, so it's a scalar random variable. Again, I multiply it with a imaginary unit. I take the exponential, something which has absolute value 1 on the unit circle, and then I take the expected value of that. Okay, so that's something now which is defined. Sorry, it should be u here. Okay, I'm sorry, that should be a u. So this eta should be a u. So this function is now defined on the dual space. So this works for infinite dimensional abstract vector spaces. This is something which you can use to characterize your random field. Okay. Good. Now, what I'm showing here now is a little example of random fields. Okay, so these are random fields which were constructed by Dichilieu, a postdoc here, who they were constructed by the Cahun-Loew expansion. Okay, and the difference you see here is, I have to explain what this is. We'll see this later here. So it's something which scales the difference between x and y, and that's called the correlation length. Okay. So essentially what we did in the Cahun-Loew expansion, let me go a few slides back to the Cahun-Loew expansion. Here we have one. Okay, so what is changing now is actually we keep these VMs. These are the expansion functions now. They turn out to be functions. Okay. We also keep the random variables from picture to picture. Okay, we see one realization. But what is changing is these lambda m's. The spectrum is changing. Okay. And this is how you happen to get these different pictures. Okay. So this is a random field with a short correlation length. Yeah. So it varies very quickly from space to space. And this nu tells us how rough it is. So nu small is a rough field. Okay, and you can see here as we stay here with the same correlation length, but decrease the roughness, make it smoother. Okay, nu equal to infinity in this case, where these are so-called Martin correlation functions. That's a certain class of correlation functions which were used here. Okay, so nu equals to infinity would correspond to a very smooth field. Okay, but you see how this, when you blow it up, maybe I have to blow it up. Okay, blow it up even more. I hope you can see it, how it gets rough, smoother as you go along here. Okay, see the edges are not as rough, they're blurred when you compare this picture to this picture here. And what we do here, going down in the column, this correlation length is increased. Okay, you see what that looks like. The correlation length, so to speak, how this correlation tells you if something is yellow here, how probable it's that's yellow at a neighboring point. Okay, and this length is larger, well, then this probability it's also yellow is on a larger extent. That's why the yellow patches are bigger here than here. There's green in between here, especially if you look here. Okay, so this patch would be here, and here it looks like this here. And then, of course, this one here is very smooth and large correlation length. And you see how this looks completely different than this here. The only thing which was changed in the KLE, in the Cahun-Loew expansion, was the spectrum. Okay, good. Now let's see how this works out for random functions. Okay, so we want to look at the covariance in the case of random functions. So we take as a space U, we saw how to do it abstractly, okay? But now we want to do it concretely. So let's say this is L2 of RD. RD is the space where we want to model our random field, okay? And we have a random variable which takes values in this space here. So it's a random field, okay? And we know this defines a linear map. This is what we've been doing before, okay? This linear map here, okay? And this linear map is given by this inner product, and this inner product looks like this here. That's the L2 inner product. Okay, so you see it's a weighted average of these random variables. Okay, let's call this random variable rho u, okay, because it depends on this u. Okay. Now the covariance operator was formally defined like this here, okay, and let's write this down here and start computing what it is. So what is this guy? Well, we know R of u is this little r rho u. So we take rho u times rho v and then take the expected value. This is what this inner product is here, okay? Now we write down what rho u and rho v are. Rho u is this, rho v is this here, okay? This is exactly how this was defined here, okay? And now I exchange these integrals and the expected value, which is also an integral. I pull it to where the random variables are. I pull the things which are not random, like u and v, I pull them out, okay, and I get this here. Okay, and you see I've already marked something blue here, okay? This integral over x, okay? And if I call this guy here, we remember this guy here is actually the correlation function. So that's what I can write in here. So this is the correlation kernel here. And you see now why it's called a kernel. Not only is it a reproducing kernel in the sense of reproducing kernel Hilbert spaces that we saw, but it's also a kernel of this integral operator. And of course, this integral operator is exactly CR applied to U. So this operator CR turns out to be an integral operator with kernel CR. Okay? Good. So now we know what it looks concretely like, what it goes. And this is now, of course, we saw we need the eigenfunctions, the eigenvectors of C we need, and we need the spectrum, the eigenvalues of C. Okay, and now we have to, that means we have to compute the eigenvalues and the eigenfunctions of this integral operator. This is, we need to do this to do the Cohen-Loew expansion. Okay, so if I write this down here, so this is the eigenvalue problem, and it's a Fredholm integral operator. That's the eigenvalue problem for this covariance kernel or correlation kernel here, okay, and it gives us the eigenfunctions Vm of x. Okay, so this equation has to be solved. Okay, and of course, because this kernel is symmetric and positive definite, the eigenvalues are positive. This is what we saw already. We know this in the concrete case here now, and if I can normalize the eigenfunctions, okay? And these random variables from the Cohen-Loew expansion, how do we get them? Well, I get them by projection, which I said before, okay? I get them like this here. And what does this mean here? Well, it's like this here. These are just these weighted averages of the random field with the eigenfunctions, and then divided by this here so that these have variance 1. They have expected value 0 and variance 1, okay? So that means they are uncorrelated random variables. Now, I can write, actually, we wrote the spectral decomposition of the operator C. We can write now the spectral decomposition of the kernel here, and it's very famous. It's called Masse's theorem. So it's more than 100 years old. The theorem on how to decompose a symmetric kernel like this here, okay? And this leads to the Cohen-Loew expansion now for this random field. So it has these eigenfunctions V, which come from here. It has these random variables, which come from here, okay? And here, then we have the square roots of these eigenvalues. I can take the square root because it's positive, okay? So again, this is an expansion in the most important. The first one is the most important if I order them by decreasing size, okay? The second one is the second most important, and so on. And it's linear in these SM, okay? Unfortunately, these SM are only uncorrelated. They're only orthogonal, but they're not independent. And again, I can expand these guys in a PCE, as I was telling you before, for just when it was a vector, this U, okay? Good, so, and for our computations, we will do this, and then this expansion is inserted here. But the good thing is now we need fewer random variables, okay? This sum, of course, goes to infinity normally. Of course, we will truncate it for computational purposes at some r, okay? So now just let us do a recap what we have to do to compute our model problem, okay? Remember, our model problem had this conductivity, which was the parameter, and normally we will see this, I think, tomorrow, why we take the log, okay? Because we don't have a constraint that it has to be positive. And that's the main reason, okay? And similarly, assume the right-hand side. It's not important here right now. We'll just stay with this one here. So now this is a random field, okay? So how I start, I expand this in a truncated KLE, yeah, of length D. Okay, so this is the KLE expansion. This is the mean. And this is the KLE expansion of this random field, the log of kappa, okay? And it has eigenvalues here and eigenfunctions here, okay? And these eigenvalues are again ordered by decreasing size. So I stop at size D. This is how many random variables I would need, okay? This is how many He lambdas I have, okay? Now, if this is a Gaussian random field, by the way, remember these guys here were computed by projection. So if this guy is Gaussian, then of course this is a weighted average of Gaussian. It's again Gaussian, okay? So if this is a Gaussian random field, then these random variables He lambda, which are uncorrelated, they're Gaussian, and they are uncorrelated normalized. But for Gaussians, we know if they're uncorrelated, they're also independent. So in this case, the He R's are IID Gaussians of mean 0 and variance 1. Okay, and we're actually finished. We don't have to do a PCA expansion because each PCA expansion just has the linear term, which is the He lambda. Okay. Now, if Q, the log of kappa, is not Gaussian, by the way, if Q, the log of kappa, is Gaussian or normal at each point x, we call kappa a log normal field. Okay, this is because the log is normal. Okay, good. But it may happen that the log of kappa is not Gaussian. Okay, so for a non-Gaussian Q, we have to transform these uncorrelated He's into independent ones. Okay, independent Gaussians. And we saw before on how to do this. Okay, so we take the space spanned by this here, then I pick and I change this one into a Gaussian, and that's the first one, and then I orthogonalize the rest with Gauss-Schmidt, Gram-Schmidt orthogonalization, and so on. Okay, and I get orthonormal Gaussians. And orthonormal Gaussians are not only uncorrelated, but they're independent. That's the characterization of Gaussians, actually. So the only random variables which have this property. Okay, so I have now, and this D random variables. Okay, so this theta space is equivalent to R to the power D, and our multi-indices alpha only have length D now. I can now take M polynomials, okay? And then I expand this guy here and these M polynomials. Okay, and I insert this here in the KLE here, okay? So this is what you see here. This is the sum here. I've already exchanged the two sums. I pulled this sum in the middle, and I pulled here. So what you see here is a kind of a reduced PCE with these vectors here, which come from the KLE. Okay. Good. And now, so that's the input to my problem. Now I make an ansatz for my state, for my solution, and I will say, okay, well, this is a PCE in the same functions here. Well, that's reasonable to assume. Okay. And then I solve this here. We've seen how to solve it by collocation, projection, or Galerkin methods. We'll see a little bit later tomorrow on Galerkin methods. And you get these coefficients, the U alpha, okay, which I've put here into this tensor. So this tensor characterizes the solution. And again, it's a tensor which lives in this space here, Rn times this here. Okay, and that will give rise to actually cutting even further down on the amount of information which you have. But if we have a PCE of this guy here, okay, that's what we get here by solving this, then we can compute a PCE of our quantity of interest, and now we have a proxy which we can use in all these integration methods and so on. Okay, good. So this was just now on how we can use everything. So we use the KLE to prepare the input, the random fields which I input. Okay, we make a PCE ansatz in those random variables which come out from the PCE of the input, or from the KLE of the input. Okay, so we have polynomials in those random variables. Okay, independent random variables. We solve for these coefficients, okay, by either of these ways, okay, and then we can compute proxies. Again, the PCE, this proxy, and now we have a cheap integrand. So this integrand is cheap to evaluate, so we can compute the expected value of that and whatever. Okay, good. So, so this is like a dimension reduction. Okay, so in other contexts, this is called a proper orthogonal decomposition, or POD. Okay, and this is exactly the same thing as the singular value decomposition of this mapping RQ, which corresponds the linear map corresponding to this Q. Okay, so to each random field we have a linear map. Okay, and the SVD of this map gives the POD or the KLE. And we've seen here with combining with the PSE expansion, we get something like this. So these vectors Q alpha is exactly this guy in here. So I sum over L, so L is gone, and the only thing is left alpha. So this gives you a vector Q alpha, or here a scalar. Sorry, Q alpha should be Q alpha of X. It's a function, okay, because this depends on X. Oh, it is a function here. Sorry, I didn't see it. My point was on it. So these are functions of X, and these are the coefficient functions of these polynomials here. Okay, so this is an expansion in discrete white noise, because we have just a finite number of IID Gaussians, okay? But it can also be given as a filter, okay, on a white noise field, okay? So we take a Brownian process, okay, a Wiener process on the space of X's, okay? And we know the generalized derivative is something like white noise, okay? It doesn't exist as a real derivative, but in a generalized sense, one can take the derivative. What comes out is white noise, okay? But we're not interested in. We take this smooth white noise. We take a mollifier function Q. So that's a function which is smooth and which drops off as x goes to 0, as x goes away from 0, okay? So it drops to 0 as x goes away from 0. Yeah. And so you integrate this guy here to a convolution with this mollifier. Yeah, it's called a mollifier because it makes this very rough white noise here smooth. Okay, so this, by the way, is called an Ito integral. Okay, so it's another way to generate a Gaussian random field. Okay, and this would be the mean function because this guy has mean 0 here. Okay, and what does the covariance guy of this look like there? What looks like this here. And you see, this is already a factorization of this guy here, but now written as an integral. And so this is why this can be generated. And again, I could do a KLE now of this guy here. Okay, I'll not go into that. What I'm going to show now in the last couple of minutes is now examples of random fields. Okay, so now it's something similar to what you saw. Again, a Gaussian scalar random field, okay? In 2D, again, with different smoothness, it becomes smoother this way here, and it becomes, correlation length gets larger this way here. It's the same random variables in each instance. The only thing which has changed is the eigenvalues, the spectrum which was going there, okay? That's the only thing which has changed as you change these guys here. And you see how this is much smoother than this guy here, okay? And what we did here, we changed this Martin covariance by adding a wavy pattern. And you see this becomes more wavy as the picture I showed you before. Right? And this is how you can introduce structures in your random field. You will see more example of this here, okay? Good. And we can also generate random fields this way with different distributions, okay? So we generate Gaussian random fields. That's the simplest because the KLE just has one, the PCE has only one term. Okay, that's this here. Only the linear terms survive. Okay, so this is all. I would just take linear polynomials. Is all I need for Gaussians. Okay, so I generate K Gaussian fields and I do a local transformation. I just put them into some function. I get a new random field, okay, which is a different distribution at every point. This at every point has a Gaussian distribution, a normalized Gaussian, okay, or not normalized, sorry, not necessarily normalized. And now this here may be something different. And for instance, if you take this, you take 4 Gaussian fields, take the product of 2 and subtract another product of 2. This is a Laplacian field. Okay, you can look up in Wikipedia the Laplacian random variables, what they look like. Okay, so and this guy taking the absolute value of that, that's an exponential distribution, okay? So that means this RE at each point X has an exponential distribution. So this is how I can take random fields, Gaussian random fields, and build other random fields which have other probability distribution at each point, okay? I can take the product of 2 of them. This is called the product normal distribution, okay? I can divide them because, of course, you can realize that this has become singular because of this. This can be 0 here. Of course, this is a very wild here. It has a Cauchy distribution. And the Cauchy distribution, if you look it up, so you look at all of them up, maybe in Wikipedia, what they look like. The Cauchy distribution is one which has no mean and no second moment. There's no moments. Okay, it's very wild random variables. Okay, we'll see this when we look at this. From these random fields, we can generate binary random fields, for instance, when you have 2 materials mixed, by taking level sets of such a random field. So we take such a level set up to level C, it's one thing, and from level C onwards, it's another thing. Okay, so this is the function which is 1. If it's below C, this random field, and otherwise 0. Okay, so let's see what this looks like. Okay, so this is a Laplacian Gaussian random field. Again, increasing smoothness here. and increasing correlation length as we go down here, okay? And this is how these binary fields look like for different cutoffs, okay? And you see, this is the rough one. You see how this is much rougher than this here. And you see how the correlation length is higher down here than up there. Okay, here it's 1, there it's 0.5. So this is twice the correlation length. Okay, so the yellow thing would be one kind of material, the blue one would be another kind of material. Okay. Now it's an exponential random field. Of course, this only has positive values. That's why you don't see anything on the negative side. Okay. So again, smoother this way, larger correlation length this way. Okay. You get all the slides, you can look at them at larger magnification. I won't do it here because it takes too much time. The binary fields coming from that here look like this. Okay, again, you see more smooth and larger correlation length. Okay, and the structures, of course, here they are much bigger than here. Yeah? Here, many little pebbles, and there's big things like here. Okay, good. This is a product normal field. Again, increasing smoothness, increasing correlation length. And this is the binary field, what it looks like. The binary fields look very similar, although the random fields are very different, okay? There's a theory which explains this, but I will not go in it. Now you see the Cauchy random field. And you can see this is absolutely wild. You see the scale is completely different. Before it was between, I don't know, plus and minus 5 or so. Now it goes up to 10 to the 4. So almost everywhere is 0, and at some point it's huge. Yeah? This is because it's such a wild random variable, okay? But the binary fields look very similar to the ones before, okay? Good. Now, things which are not isotropic, okay? So you can see now we can do now something which has, let's say, fibers in this direction. Again, it's getting smoother this way, and it's having larger correlation length this way, okay? And it's a Gaussian random field, okay? But now the correlation function is obviously not isotropic. Huh? It is different in this direction, in the y direction, than in the x direction. This is how you can build random fields with structures in there, okay? So random fibers, let's say. Okay. Now this is with larger waves, so to speak, okay? And their cutoffs, what they look like. And you can see that there's an orientation of these guys here now, okay? They're oriented in this way. Now comes the same thing in 3D, okay? So these wavy things, you can see they can produce very filigrane structures here, and now getting smaller and smaller correlation length. You get little tubes here, or little spaghetti. You can say it's a lot of spaghetti here, okay? By taking a different correlation functions, we get a lot of pebbles, okay? As cutoffs. Now this is binary fields in 3D, okay? There's a few more here now where you can see this is binary fields generated with increasing smoothness and increasing correlation length. You can see the pebbles are smaller here than here, okay? So they're smaller here than here because the correlation lengths, and they're rougher here than here because here they're rough and here they're smooth, okay? Here's another example, okay, with another correlation function. And now somewhere we again generate little spaghetti, so to speak. Okay, so this is very anisotropic random field now. Yeah, so now there's broken spaghetti, so to speak. And I think this is probably the last ones here. Okay, just let me summarize. Okay, we've seen that we can look at random variables as random fields, as random variables with values in a vector space. And there's a one-to-one correspondence with linear maps, and this defines the correlation and covariance operators. And the analysis of these linear maps, this led to the Cahoon-Loew expansion, or similar separated tensor-like expansions, okay? And the uncorrelated random variables which appear here, so this is a dimension reduction, now truncating this at a nice point. They can expand this further in independent random variables, but now these are the important random variables. So we call it polynomial chaos expansion, for example. And this expansions we can use to compute with random fields, as you've seen. So I've shown you a lot of random fields which can be used as inputs to computations. Okay, so let me finish here. I'm sorry I'm gone 7 minutes or 8 minutes over the time, 9 minutes actually. So maybe we should start 10 minutes later for that. So instead of 10:30, we'd start at 10:40. Is it okay? So now I would ask, is there any questions now to what I've been telling you? I don't see anyone writing anything. So if there's no questions now, then I think we can all go and have a sip of tea or something like that. Okay, and then we'll come back in 20 minutes. Okay, so this is, so it's 10:20 now. In 20 minutes, it's 20 minutes to 11. Okay, or 10.